So welcome everyone to the Combinatorics Physics and Probability seminar. It's a pleasure to have you here. So this week we have Francis Brown from University of Oxford and All Souls College talking about modelized space of tropical curves, graph Laplacian and physics. So after a couple of weeks talking about amplituhedra and positive geometries, this time we are still talking about physics in relation to scattering amplitude somehow, but more in terms of Feynman diagrams and Feynman integrals. So in connection with arithmetic algebraic geometry, tropical geometry, and combinatorics. So feel free to start.
Great, thank you very much for the introduction and for the invitation. So I gathered from your email that you've been, as you said, studying amplituhedra and positive geometries and so on. And so in the light of your email, I thought, rightly or wrongly, that it might be a good idea to step back a bit and give some a sort of general introduction to what's done in particle physics and how it's connected to combinatorics in the first place. So I don't know if that's the right decision. I wasn't sure who the audience was. So forgive me if this is all very clear to you. But I thought I'd start at the beginning, and this is going to be quite, what's the word, sort of vague. It's going to be a sort of overview of how these things come about. So I've got quite a long introduction before I get to things I'm actually working on. But the bottom line for why combinatorics arises in physics, in high energy physics at all, is because we're interested in particle scattering. So I don't know. I think can you see my mouse when I do this? Can you see?
Yes.
Yeah, you can. Brilliant. So particle scattering leads to originally what are called Feynman graphs. So here's a diagram of some particle scattering. We imagine time going up vertically from bottom to top, and we have two particles coming in on the left and right at the bottom, maybe electrons. And as they get close to each other, they exchange a photon, this wiggly line, and they exchange some momentum, and so they bounce off in perhaps a different direction with a different momentum. And so this particular process between particles is represented by a graph. Okay, and we can have much more complicated graphs that we try and draw, and you could have the same picture. But what could happen is that the photon spontaneously produces a pair of particles like this, an electron and positron, that will annihilate. And this will be considered as a sort of higher order correction, higher order quantum contribution to what you observe, which is the scattering of two electrons. Okay, so that's very simplified, but what we do as a mathematical formulation of this is we consider connected finite graphs. Okay, they often have external legs, or more precisely external half edges, and these correspond to incoming and outcoming particles. And instead of having these wiggly lines and straight lines of different types, it's simpler just to draw all edges as straight lines for simplicity. Okay, so each graph represents some interaction between particles, and what's known as Feynman rules, in this case, is a way to assign to a graph a complex number, or typically actually this is a function of the masses and the momentum of the incoming particles. And it's really a recipe which takes a graph and gives you some quantity. And that involves integration. And it's very complicated. And the whole challenge is to try to understand this better. Okay, so some more vocabulary. We have the amplitude then normally means the sum of all possible graphs. So typically the sum is infinite. It's not really known whether the sum converges or not. There are a lot of subtleties. It's not known if it's even resummable, Borel resummable. So typically what one does is one sums over graphs of sort of loop order by loop order. And one hopes that this quantity converges in some sense. Okay. And then what you do is you take your amplitude, which is a complex number or complex function, and you take its norm squared, and then that essentially gives you the probability of observing that in experiment. Okay, so that's extremely heuristic. And I apologize, I've sort of done such a high-speed introduction to a huge subject, but that's essentially the gist of what's going on. So that in modern approaches to quantum field theory, one tries to simplify this because the number of graphs is absolutely colossal. What one does then is to simplify this by packaging, in some sense, infinitely many graphs together, or infinitely many integrals together. But the upshot is that one still encodes the resulting quantities by graphs, maybe graphs of a different type, such as you may have seen Playbit graphs or other types of graphs. But the bottom line is we still have graphs, and the graphs encode integrals. So from a mathematical perspective, nothing has really changed much. We've got graphs, we've got some quantities. It's just the Feynman rules have changed, they've become different. Okay, so but in all these settings, the philosophy is the same. Okay, so graphs. I'm going to take, as I said, finite connected graphs. I will denote by lowercase, e.g. the number of internal edges. So of course, graphs have internal edges and external half edges. So e.g. is the number of internal edges. Hg is the rank of the first Betti homology of the graph, which is a free Z module. So in physics, it's called the number of loops, of course. I will allow, we do allow self edges. So self edge is also something like this. It's called a tadpole in physics, if you haven't come across that terminology. In this context, the usual way to encode external half edges or legs is via a map. So you have n external half edges. It's a map which maps the integers from 1 to n to the set of vertices. So in all this business, the half edges are always labeled, right? So automorphisms of graphs will not allow you to permute the external edges in general. So each index I encodes a particle which carries a momentum. So this momentum is q sub I, and it's an element of Euclidean space R to the D. Now D is fixed, and it's typically known as the space-time dimension. It's typically an even integer. And the final piece of data are particle masses. And so these are masses assigned to the internal edges of the graph. And one way to encode this is as a map, M, from the set of edges into a finite subset of the real numbers. So why is it a finite set? Because we're thinking of a physical theory. Say you have an electron, electrons in your theory, or other particles. They have fixed masses. And so the sort of mass is some fixed number, and then each edge gets assigned the mass corresponding to what type of particle it is. So it's like coloring the edges. Okay, so here's an example of the graphs that I want to consider. There are two types of edges. You see there are three internal edges. Let me just label them. The internal edges are these three ones. The external edges are half edges. They will always be oriented inwards. The reason for that is because a particle going out is the same thing as a particle coming in, but with the negative momentum. So you can always assume all your particles are pointing inwards, makes life easier. And there's one condition that's important, which is momentum conservation. That's that the total momentum entering the graph is 0. So that's very important. And as I mentioned earlier, it's a huge program to try to understand how the combinatorics of such a graph governs the Feynman integrals that are what you need to compare to experiment. And when I say it's huge, I don't know how, this must be thousands of people have worked on this since the 1950s or so. I think we're very far away from understanding this completely. So a quick review of Feynman integrals. So this is very classical. It's the classical presentation of Feynman integrals as you find in textbooks. Essentially, there are three different main ways that Feynman integrals are represented. Position space, momentum space, and parametric space. So in quantum mechanics, you want to average over all possibilities. You integrate over space of possibilities. Those possibilities could be the positions of your particles. That gives rise to position space. They could be the momentum of your particles. It's momentum space, and the two are related by Fourier transform. But I'm going to talk about a third called parametric space. And that's much closer to combinatorics. So in parametric space, we think of the edges of the graph as having lengths. So each internal edge of the graph has a physical length, it's a real number, and that can change. And the integrals will be over all possible lengths of these internal edges. Okay, so more on that later. So as I said, each internal edge is assigned a parameter called a Schwinger parameter. And later on, it's going to be a positive, a non-negative real number. For now, it's just a variable. And then here's the shape of the Feynman integral. So I've been told I shouldn't do too much differential geometry or integrals or things like this. So I'm just flashing it up, and I want to talk about the ingredients that go into it and not say too much about it. It has the following approximate shape. That there are some prefactors, some gamma functions, and constants I want to ignore. Then, as I said, it's an integral essentially over the space where all...
What's up?
Hello, is there a question? No, okay, I'll continue. So it's an integral over the space where all the these parameters are positive. Then you've got some standard integration measure, omega g. Some numerator, which is a polynomial in these edge variables. So we could take 1 in the first instance, just the polynomial 1. But for realistic quantum field theories, they're very complicated numerators. And then the thing I really want to focus on are these two polynomials in the denominator. So all the sort of, the difficulty lies in the denominator. The numerator is a bit of a sideshow. And there are two main ingredients, polynomial psi g and a polynomial I call psi. Now the polynomial psi g is very old. It goes back to Kirchhoff in the 1840s in his study of electrical circuits, and is very well known in combinatorics. So in physics, it's called the first Symanzik polynomial. And somewhat bizarrely, it doesn't depend on what's called the kinematics of the graph, the momenta or the masses at all. It only depends on the sort of core topology of the graph, which is slightly surprising, but that's the way it is. So the graph polynomial psi g is defined to be the sum of all spanning trees in the graph. And then for every spanning tree, you take the product of these alpha variables for all edges not in the tree. So that's a polynomial in the edge variables alpha e with coefficients in z. In fact, the coefficients are all 0 or 1. So spanning tree is a subgraph that's a tree, it's connected and has no loops. And spanning means that it contains every vertex of the graph. So this polynomial is homogeneous of degree hg, and it does not depend on external half edges or masses. So of course, this is part of a huge business in combinatorics with Tutt polynomial, multivariate Tutt polynomials. This is a variant of that construction. Now, the second Symanzik polynomial, which I remind you is the other essential ingredient in this integral, psi. It is slightly strange in that all the dependence on the masses. Well, it essentially has two terms. All the dependence on the momenta is in one term, and all the dependence on the masses is in this second term here. And the mass dependence is extremely simple. It's just this linear form in the alphas, sum me squared alpha e, times the classical Kirchhoff polynomial. And then all the dependence on external particle momenta is what's called, well, this polynomial called phi, and it is defined as follows. You now take the sum over spanning forests with exactly two connected components, T1 and T2. So T1 and T2 are trees. Then as before, you take the product of all the alpha variables not in the tree, and you multiply them by this factor, which is the dot product of all the momentum entering the first tree with all the momentum entering the second tree. So the dot product here is the Euler product. Here, if I've got two vectors, x1 up to xd and y1 up to yd in Euclidean D space, then x dot y is just the usual Euclidean product, component by component. So that's a definition. And so it turns out that psi and phi are homogeneous polynomials of degree 1 more, the loops plus 1. So let me, I think I have a bit of time, let me actually just do some examples because it's fun. So let's take this graph, which has 3 incoming momenta and 4 edges, 2 loops. So the spanning trees are connected subgraphs, which are trees which meet every vertex. The first one is consists of edges 1 and 2. And then corresponding to that, we get a monomial, which is the set of edges, internal edges not in the spanning tree. So we get alpha 3, alpha 4. Another spanning tree is edge 1 and edge 3, which passes through every vertex. So the complement of 1, 3 is 2, 4. We get alpha 2 plus alpha 4. Then 1, 4. So that gives us alpha 2, alpha 3. 2, 3. Alpha 1, alpha 4. And 2, 4. This gives plus alpha 1, alpha 3. And clearly, it doesn't depend in any way on momenta Q or the external leg structure. It just depends on this graph here in which I've removed the external legs. So that's the Kirchhoff polynomial, again, very well known, used very widely in mathematics in a variety of different fields. This polynomial phi g, however, is not at all so prevalent. So let's do it. We now need to look at spanning trees with 2 connected components. So here you're allowed to take spanning trees which reduce to a single vertex. So here's one. If we take this vertex and edge 3, then that has 2 components. It's a 2 tree, and it meets every vertex of the graph. And so the next thing to do is to look at the momentum that each tree inherits. So we have Q2 coming in here, Q3 coming in here. And what we do then, the recipe was minus the momentum entering the first tree, one on the left, let's say, times where times is the Euclidean dot product, Q2 plus Q3, which is momentum entering the second tree on the right. But remember, by momentum conservation, we demanded that the sum of all momenta add up to 0. So this is just the same thing as Q1 dot Q1. And then, so that's the coefficient in front of the corresponding monomial in the alphas. And as before, we take the set of edges which are not in the spanning tree. So that's 1, 2, 4. And that's our first contribution to the polynomial phi. Here's another spanning tree, so we can do this one now with edge 4. Again, we have to look at the momenta coming in. It's exactly the same as before. So we're going to get plus Q1 dot Q1, alpha 1, alpha 2, alpha 3. And then there are two more spanning two trees, this one and this one. So this is edge 1 and this is edge 2. And so again, in the same way, we look at the momenta going through each component. And here we get Q3, because we've got a Q3 coming in here, dot Q3, alpha 2, alpha 3, alpha 4. And then the final one, so I've run out of space. Oops. Let me get rid of this, it's annoying. And this. And so then the final term, I'm still out of space. The final term is Q2 dot Q2, then alpha 1, alpha 3, alpha 4. So that's the polynomial phi q, which has 4 terms. And then the polynomial that we really care about, psi, is phi plus some linear factor times this polynomial psi. Okay, so that's all the combinatorial content of Feynman integrals boils down to these polynomials. Okay, so they have some very basic properties. The first one, very well known, again, in the field of, in the area of polynomials and so on, contraction and deletion is extremely widely used. So what it says is if you take a graph polynomial psi g, then, and pick any edge in it, then you can always write it in the form alpha e, the corresponding edge variable, times the graph polynomial of the graph in which you deleted the edge e, plus the remainder term, which is the graph polynomial in which you've contracted the edge e. Okay, so this is, again, very well known, this relation. There's some caveats. It could happen that when you delete the edge, for example, if it's a bridge, that your graph becomes disconnected, then you have to define what it means for the graph polynomial of a graph with many components. And here it's just the product of the graph polynomials of each component. Another caveat is that if you have a self edge or tadpole, if you contract it, you want this to be 0. So the way I denote this to avoid confusion is with a double slash. This means contract the edge e, but if it was a self edge, you just get the empty graph. The polynomial phi has a similar property, and from this you deduce a property for the polynomial psi, but it's alas a little bit tricky because it's not linear in each variable alpha e. You can have alpha e squared, so it's very easy to derive, but it's slightly more complicated. Okay, so here's another extremely important property, which I call asymptotic factorization. And this does not seem to be very widely known at all. Even in physics circles, there's some obscure papers in the 60s where some of this was first written down, but it's not been systematically used. And it's actually quite surprising. So now, if you take any subgraph of your graph G, we can consider the subgraph, but we can also contract all the edges in gamma. Now, in this case, contrary to the double slash notation, when I contract a graph, I'm going to contract all the edges, irrespective of whether they are self edges or not. We just don't care. So you contract all the connected components of gamma become points, become single vertices. Okay, so what happens then is that morally the Kirchhoff polynomial, graph polynomial, wants to be the product of the graph polynomial of the subgraph times the graph polynomial of the quotient. But it's not quite right. There's an error term or remainder term R, and this remainder term is small in some sense. So it's small in the following sense, that if you take alpha E, all the variables corresponding to your subgraph, and let them become very small, to order of epsilon, then psi is going to be order of epsilon to the number of loops in gamma. But then the remainder term R is going to be of even smaller. It's going to be of order one smaller order. So so it says that as the variables alpha E for the subgraph go to 0, the remainder terms goes to 0 even faster. And there's also an asymptotic factorization for the polynomial xi of this form. I like to call these ultraviolet factorization formulae. There's an extra one for the polynomial xi called infrared, which I haven't written down, but it has yet another factorization formula, which is interesting. So what that means is that, as I said, if you take the subgraph, a subgraph of your graph, gamma, it could be any subgraph, and think of the edge variables becoming very small, in the limit, asymptotically, the graph polynomial factorizes into the subgraph and the graph obtained by contracting the subgraph. And that's true for both these polynomials. So let me illustrate that, because it's actually quite surprising. If we take just this graph, since I'm only going to illustrate this on the graph polynomial, so no external legs. This is the graph polynomial here. We worked it out earlier. Now, if we can take any subgraph, but if we pick the subgraph with edges 3, 4, then the graph polynomial of this graph, subgraph 3, 4, is alpha 3 plus alpha 4. Now, if we contract edges 3 and 4, we get a graph that looks similar, whose edges are labeled 1, 2. And this alpha 1 plus alpha 2 is its graph polynomial. And you'll notice that the full graph polynomial is the product of these two contributions, which gives 4 of these terms. And there's a single extra term, alpha 3, alpha 4. Now, why is this a remainder? Because if alpha 3 and alpha 4 were of order of epsilon, this is of degree 1 in alpha 3 and alpha 4, then the remainder term would be of degree 2 in epsilon, it'd be epsilon squared. Okay, it's degree 1 higher. And so in the limit, you can sort of discard the remainder term. But what's amazing about this is it works for any subgraph. So you can pick the subgraph 1, 2, 3. You get a different asymptotic factorization that I've written here. This is the graph polynomial of the subgraph spanned by this triangle 1, 2, 3. If you contract that, the quotient is just a single self-edge graph 4. This is the product of their graph polynomials. And the remainder term is here, which looks wrong. I think I made a mistake. I've got an extra one too many terms there. Let me correct that. So this is shouldn't be there. It should have 2 terms. So this asymptotic factorization is an incredibly strong constraint, and in fact, it essentially uniquely determines these graph polynomials. So if you were to say, I would like to associate to graphs polynomials that satisfy this factorization property, then you're pretty much forced to consider psi in the first instance, the graph polynomial. If you then try to solve the same problem, but with a polynomial of degree 1 higher, you find that, you get a sort of, they're all inductively determined by some sort of trivial graphs like a vertex or a single edge. And you have freedom to choose what they are. And those are called, that is called momentum and masses. So that the momenta and the masses emerge as the initial conditions in the problem, the sort of inductive system of constraints that the asymptotic factorization imposes on graph polynomials. So I don't think this has been exploited much in mathematics. I'd be very interested to see if it holds for touch polynomials and other applications outside physics. But in physics, it's used primarily in the theory of renormalization, but only partially. So there's a lot of extra structure there. Okay, so now actually, after a very long introduction, I want to get to what I was hoping to talk about, which is the moduli space of metric graphs. So I gather you've seen in previous talks this amplitude-hedron program where you have a space that's indexed by the sort of cellulated by regions that are indexed by graphs, and ultimately you want to consider sort of integral or differential form on each region, and they package together to form an amplitude. So here I'm going to do something quite similar in spirit, but just for classical Feynman graphs. And the space in question is something extremely classical. Well, it's not extremely classical, it's quite classical. It's the tropical, the moduli space of tropical curves. Another reason why this space is interesting is because it's very close to string perturbation theory, which is a different part of physics where you have identical combinatorics, which I'm not going to talk about. So in brief, what is a tropical curve? Well, so the quick definition is to say that it's just any connected, weighted, stable metric graph. So let me go through those adjectives in turn. Weighted means that the vertices carry weights to non-negative numbers. We don't particularly care about the weights. All the graphs we've seen so far and are fundamentally interested in have a weight 0 at every vertex. However, you need to consider graphs with higher weights at the vertices because that records what happens when you contract tadpoles, self-edges. Okay, then stable, again, is a very mild condition. We can ignore it in the first instance. It comes from algebraic geometry. But it says that every vertex of weight 0 has to have at least 3 edges coming out of it. And those edges can be half edges, they could be internal edges or external half edges, it doesn't matter. Likewise, every vertex of weight 1 has to have degree at least 1. So it's a very mild constraint indeed. Now, the important thing here is the word metric. Metric means that every internal edge of the graph is ascribed a length. And that length is a non-negative real number. It is normalized if the sum of all the edge lengths is 1. Here I've skipped over quite a few things, but one way to think about the edge lengths is as follows, that normally one only allows edge lengths to be positive. And then you say that if an edge length goes to 0 and the edge length becomes actually 0, that's equivalent to the metric graph in which you've actually contracted that edge. So if you think of the edge lengths as being physical lengths of the actual edges, then it's reasonable to think of edge length 0 being the literal contraction of that edge. And that's what's going to happen. So I'll make that more precise in a minute. To make the contractions a bit more precise, we have, in general, we have vertices with weights here, W1 and W2. So if we contract this edge, then they come together and form a vertex. And that vertex has a new weight, which is the sum of the weights of the original endpoints of the edge. And as I mentioned before, when you contract a self-edge or a tadpole, then it disappears, but the resulting vertex gets weight +1. So the weights are bookkeeping exercise to remember what's happened to the genus or the loop number of the graph. As you successively contract edges, loops may disappear, and the weights record what's happened to them. Okay, so from this, you can form a category, IGN. And the objects in this category are weighted, stable graphs with a fixed number of external legs and G loops. Notation G comes from algebraic geometry, where we think of curves of genus G. Now in this category, there's no metrics in this category, they're just combinatorial graphs, right? So this category sort of encodes the combinatorial types in the first instance. So those are the objects, the finitely many objects. And the morphisms between these graphs are isomorphisms and contractions of edges, which we discussed back here. So the weights obey these rules. So that's a category with a finite set of objects and a finite set of morphisms. Now from this category, one constructs a space called MGN trop, the moduli space of tropical curves of genus G with n points. Again, I'm going to be very vague about this in the interests of time and because I don't want to get into too many topological details. But the quick way to define this is simply as a functor from the opposite category of IGN into a certain category of cones in a Euclidean space. So these are sort of very nice convex regions in Rn, some n, and the maps between cones are really inclusions of faces of cones. And what we do then is for every such graph in this category IGN, you associate a cell. That cell is denoted CG, and it's simply the space of all possible edge lengths of the internal edges of the graph. So it's the real numbers to the power, the number of internal edges. Sorry, put non-negative real numbers to the power EG. And then what we do is then glue all these cells together according to the morphisms in the category IGN. And so the high-speed way to do that is simply to define MGN trop as the inductive limit or co-limit of, so as a typo, this should be CG of the cells with respect to the morphisms in this category. So to make that a bit more concrete, an equivalent way to define it is to take these cells CG for every graph in your category IGN, so the fixed number of loops, fixed number of external edges, and then impose an equivalence relation upon these cells. All right, so an object a point in MGN trop is given by a graph, an equivalence class of graphs with edge lengths, a point in CG, in other words, of a metric graph. So the equivalence relation is generated by the automorphisms of the graph, and we identify the component of the boundary of the cell CG. So I remind you, CG was the set of all possible edge lengths. And as I said earlier, as one of the edge lengths goes to 0, we identify that with the corresponding cell of the graph in which that edge is completely contracted. So I mixed my notations. This should be the edge length L equals 0. Okay, so to make that a bit more clear, let me give some examples. So here is the case where the genus is 1, so we have one loop, and we have 2 external half edges. So the external half edges are denoted in red, and all the internal edges are in blue. So this is I12. There are exactly 5 stable connected graphs in this category. You can check, so here they are. You can check the stability. For example, this is a vertex of genus 0. It has a weight 0, sorry. It has 3, has degree 3, so that's fine. The vertices of weight 0, I just don't indicate the weight at all because it clutters the diagram. These vertices here have weight 1. They're labeled with a 1. And so these dotted lines here indicate all the possible ways you can contract edges. So let's have a look. If we start with this graph here, we are allowed to contract either one of these blue lines. And when we do so, we get this graph here, fine. When we contract this edge here, that's a self edge. So the rule is that when we contract it, it becomes a vertex, but the vertex gets a weight 1, which remembers the fact that we have contracted away a loop altogether. On this side of the diagram, again, we can contract this edge going to this graph, or we can contract this self edge. And again, that produces a vertex of weight 1. And in this diagram, if we contract this edge, then the edge disappears altogether, but the new vertex gets the weight, which is the sum of its endpoints. That becomes 1. Right, so this is very simple, but they're quite a rich structure. So then how do we get the tropical moduli space? Well, we need a cell for each space, and we glue them together. So the cells here have different dimensions. Here, we take a copy of R positive squared, because there are 2 internal edges. There'll be another copy for this graph. This graph here only has 1 possible edge length, so it gives, you get an R1. Here we get an R1. And here we get an R to the 0, which is just a point. So the space naturally comes with the stratification. And I'm going to just focus on the right-hand side of this picture and leave the rest as an exercise. So let's work out how the space looks on this side of the picture. So this graph here with 2 edges, 1, 2, as I said earlier, is assigned a cell, a 2-dimensional cell, R greater than or equal to 0 to the power of 2. And points in this cell correspond to possible lengths ascribed to the edges 1 and 2. So we have L1 along this axis, L2. And it has 2 sort of boundary components. Let's look at the bottom one, where L2 equals 0. So L2 equals 0 is this line here, and it corresponds to contracting edge 2. When we contract edge 2, we get this graph, where this 1 means that I've labeled the edge. This is edge 1. It's not the vertex, edge 1. And in edge 1, the cell associated to this graph is 1-dimensional. It's all possible values of the length of that edge. And of course, when in the corner here, when L1 goes to 0, it corresponds to the graph we had at the bottom, which is just this graph. Now it's got a vertex of label with a weight 1. Slightly confusing, I apologize for that. And to that, it's just, we gave a copy of R0. It's just a point. So these are the 3 spaces, and we have to glue them together. Now, the first remark is that this graph up here has an automorphism of order 2, which interchanges the 2 edges. So that corresponds to a linear map on this Euclidean space, which flips the diagram along the diagonal. So let me try to draw a diagonal. So the symmetry interchanging the 2 edges is this map. And so the first thing we do is we glue this space to itself along this map, and that corresponds to taking this quadrant and folding it in 2 so that it becomes a triangle. So here I've tried to draw this triangle here. It's the cell corresponding to this graph. So it's R2 modulo L1, L2 equals L2, L1. So it's like a sort of a folded napkin somehow. And the topology is quite tricky because something interesting happens along the diagonal clearly. Then we, so that's gluing along automorphisms. Next, we have to consider this contraction of edges. So then we take the cell associated to this graph and we identify it with the line L2 equals 0. So we glue that into this bottom edge of the graph. And finally, the cell of this graph, which was 0-dimensional, just a point, gets glued into the corner. So in the tropical moduli space, these 3 graphs form this picture. It's a quotient of the Euclidean quadrant in which is glued a half line. Sorry, it's a half line and a point. And to that, we also need to glue in something corresponding to the left-hand side of the diagram. And it all fits together in a space that's quite complicated. Good. So, so that's our space. That's the moduli space of tropical curves. And I should say that there's a variant here where you have you allow masses to the edges. That just means that you're coloring the edges in different colors. It doesn't change very much to this picture, except that it restricts the number of automorphisms you can get. So the geometry changes, but the combinatorics is sort of similar. So that's something that's been studied by Birkhoff and Mühlhauser recently. Okay, so tropical Torelli map. So on the moduli space of curves, there's something called the tropical Torelli map, which is the tropical version of something extremely famous in algebraic geometry that goes back to Abel and Jacobi and so on, about which I'm not going to talk because this is combinatorics and not algebraic geometry. But we can just write down the definition of the Torelli map without worrying where it comes from. And the basic ingredient is the graph Laplacian matrix. So there's an intrinsic definition of the graph Laplacian matrix. I just gave a sort of naive hands-on definition here, just to save time. So to do this, we choose an orientation on the edges of the graph, and we choose independent cycles of the graph, C1 up to CH. And then, having done that, we can consider the incidence matrix, which is EG by HG matrix. And the entries of this matrix are just the coefficient of the corresponding edge in the corresponding cycle. And then the graph Laplacian, which is very classical, is the transpose of this matrix times a diagonal matrix DG times the incidence matrix again. The diagonal matrix is just the DG is just the matrix with the lengths, if you like, the lengths of each edge along the diagonal. Now, just a quick comment. You might be puzzled by this because in the literature there are different versions of Laplacians which have different sizes. The Laplacian sort of on Wikipedia, if you like, is what I call the dual Laplacian. It's very similar to this, but it's dual in some very precise sense. But this is the one that we want. So here's an example of a graph with two loops and three edges. I've oriented the edges, and we can take a basis of cycles, C1, this cycle here, and C2, this cycle here. So C1 is E1 minus E2, and C2 is E2 minus E3. And then the incidence matrix HG has a row indexed by every edge, columns are indexed by the cycles, and the entries are just the coefficient in these equations. So E1 occurs in C1 with coefficient 1, but it does not occur in C2, and so on and so forth. And then when you work out what the graph Laplacian is, you get this very nice square 2x2 matrix. And you observe that the determinant is well defined. The reason it's well defined is because if you were to change the choices, if you were to change the basis of cycles, you would find that the Laplacian matrix transforms via this formula, where P is a matrix in GL HG of Z. And therefore, the determinant of the Laplacian is well defined because under this transformation, it gets multiplied by the determinant of P squared. And the square of the determinant of P is 1 always. So the determinant makes sense, and it is equal to the graph polynomial. So this is a very classical theorem. It follows from a version of the matrix tree theorem. Okay, so now I want to talk about something that's in progress. There is a variant of the graph Laplacian that I call the generalized graph Laplacian, which depends on momenta and masses. And this is not something that is in the mathematics literature, but it's the thing that's relevant when trying to interpret Feynman integrals. So for simplicity, in the first instance, I'm going to take momenta in two-dimensional space-time, which I will identify with the complex numbers. And later I'll say how to generalize that. Now, the first thing we do is choose a momentum routing. So that's the choice of a momentum, which is complex, I said, for every edge of the graph. So a priori, the momenta are just something carried by the external half edges, but you can get it to flow through the whole graph by demanding that the momentum be conserved at every vertex. So here's a picture of a vertex. It'll have a certain number of internal blue edges, but it may have some external half edges coming in. And we demand that the total momentum going through the vertex is 0. And it's very easy to show that there's always a solution to finding a momentum routing, and you know exactly how many solutions there are and so on. But anyway, just pick one. And then I want to extend this incidence matrix by adding an extra column. I'm just going to add one extra column, which is the data of the momentum routing for every edge. I remind you that the rows were indexed by the edges of the graph. Then I define a second matrix, M tilde, which encodes all the data of masses, and it's just the zero matrix of exactly the same size. And the final column is just the data of the internal particle masses for every edge. And now, analogously to before, we define the generalized graph Laplacian matrix to be H transpose DH, it's the same as before, plus M transpose DM. So there's a small correction term coming from the masses. And there's a very small difference here, is it's not quite H transpose. I take the complex conjugate, so that's the Hermitian conjugate. And then the theorem is that the determinant of this matrix gives the second semantic polynomial, which is the key player in Feynman integrals, and allows us then to interpret the whole Feynman integral geometrically. Here's an example of a graph we considered earlier, but now I've added two external momenta, which by momentum conservation must be q and minus q, because they have to add up to 0, remember. So here's the generalized graph Laplacian matrix. When you work it out, it always has essentially a block matrix form. The top left-hand block is just the usual graph Laplacian. Oops. And then it's got stuff along the edges. So here, the stuff along the edges only depends on the momentum flowing through each edge. And the recipe is kind of easy, it's kind of obvious. Here it's the complex conjugate of those elements. And in the bottom right-hand corner is all the mass dependence. And it's always just the sum of all the edges times mass of that edge squared plus mu I bar, momentum flowing through that edge. And so this gives us a geometric interpretation of the second semantic polynomial as the determinant of some very natural Laplacian type matrix on graphs. Now, as I said before, the tropical Laplacian, also called the tropical Torelli, comes from something in algebraic geometry going back to Riemann called the Riemann polarization form. And in fact, I derived this formula for the generalized Laplacian from a generalization of the Riemann polarization form for Riemann surfaces with punctures. And if you do it the right way, and you tropicalize it, this immediately pops out. And by happenstance, it's fortunate enough to give exactly the quantity that is of relevance in quantum field theory. So if we want momenta in 4-dimensional space-time, you can replace complex numbers with quaternions. That's a little bit scary to do matrices with quaternions, but actually matrices with entries which are quaternions are actually very well behaved. Pretty much everything you'd like to do with them works, except determinants don't make sense. That's the only thing to bear in mind. Traces and determinants are not defined the way you might think. But apart from that, the theory goes through perfectly well. And in the quaternionic case, a special case of this construction was considered by Bloch and Kreimer some years ago, with the 0 particle masses. Okay, so here's a geometric picture before I wrap up of what's going on here. So we have this tropical moduli space, and it has these cells. And here, I've instead of taking the cells we had before with all possible edge lengths, I just normalize them so they add up to 1. So the cells now look like triangles. That's a small detail, but it's what's more relevant for physics. So we have all these cells, and on the cell, every point of the cell corresponds to a metric graph with normalized edge lengths, such that they add to 1. And on every point of this, cell, therefore we have corresponds to a metric graph. And we can consider the Laplacian, or the generalized Laplacian. And what's relevant is where the determinant of the Laplacian vanishes, so where the Laplacian becomes singular. And so there are two, there's the ordinary Laplacian and the generalized Laplacian, corresponding to, remind you, the determinant gave the first graph polynomial, the determinant gave the second semantic polynomial. So we have two regions, which is where the Laplacians become singular, drawn in red. And so we can think of a Feynman integral literally as being, it's an integral over every cell in this moduli space of some integration measure which has poles, which has singularities exactly along these red loci where the Laplacians become singular. So this is very similar to the amplitude-Hadron program, as I'm sure you've heard a lot about, where you want to interpret amplitudes in n equals 4 Yang-Mills as some kind of volumes or associated to cells in some sense. It's actually dual to this picture in a precise sense, but I won't get into that. Now the issue with this is that, so geometrically everything seems very natural, but the issue is that the integrand in the Feynman integral, if I remind you, which was something like looking like this. This seems slightly ad hoc. And this integrand, it's not clear to me at this stage how to view it as a sort of natural volume form on this space. I'm not sure if it's possible. But what we can do instead is to change change theory in some sense and try to consider what happens when we put a natural volume form here. So this is just in the very last slide to advertise what the reason why I've been thinking about all of this. And that's because on the space of matrices, there is a very natural and unique, in fact, volume measure, which has very nice properties. And it's obtained by this slightly complicated looking formula. You take the graph Laplacian inverse, multiply it by d of the graph Laplacian, raise it to an odd power, and take its trace. And this has, it's very classical, goes back to the study of the cohomology of symmetric spaces in the general linear group. And it is well defined. So it is completely independent of all choices. Whether you change basis, whether you change momentum routing, you change anything, this is pretty much one of the unique types of forms that doesn't depend on any choices. It's very natural. And therefore, you can consider integrals of the following shape. You simply just take the integral over of this canonical sort of volume over a cell of the moduli space of curves. And that gives you a canonical Feynman integral, which can be interpreted as the volumes of cells in this tropical moduli space. And that seems to me to be one of the closest analogies of the amplitude-Hadron type program in the world of classical Feynman integrals. So I think I'm going to stop there. I'm just ever so slightly over time. So it's time I stop talking and asked if there are any questions.
Thank you very much. Let's thank Francis for a very nice talk. And we can ask questions. So does everyone have any question?
Yeah, yeah, I have a question.
Hi.
Hello, hi Francis, nice to see you.
Hi.
Yeah, so if you, yeah, right. So if you restrict to tree level, of course, we have the icosahedron story, whose normal fan, I believe, would be related to the fan that you're constructing.
Yes.
Right?
Yes.
And so I'm wondering, yeah, you mentioned very briefly the amplituhedron story. Do you have an icosahedron is there a notion of an icosahedron here whose normal fan would be the objects you consider here for graphs? And is there a dual object which would compute the volume? I mean, who's, like a dual object here, like the dual icosahedron. Anyway, just.
Yeah, so you're right. I'm not sure I completely understood the question, but I can take bits of it. You're right that when you consider external legs, genus 0 becomes interesting. Of course, there are no integrals to do because the integrals are trivial in this case. I mean, there's nothing to integrate. That generalizes, yes, in the MGN trop, you can look at the combinatorics of each cell. The analog of the icosahedron is what you need to do is to do a sort of bordification of the space MGN trop. You need to compactify it in a certain way. And that precisely corresponds to this asymptotic factorization I mentioned earlier. So here you'll have to essentially truncate these bad regions where the cell meets the red lines, and you'll get a hexagon. And this hexagon will be the analog of your icosahedron. So absolutely, that goes through. You can do a bordification of MGN trop. I'm not sure what you mean about dual icosahedron. In what sense you're thinking of duals and volumes?
Well, I mean, the interpretation of amplitudes as volumes, right? So I mean, if you're your comment there, yeah.
Yeah, so, okay, well, I could say something about that, because I'm not sure if I answered your question, but
yeah.
The way I see the things going at the moment is it's dual in the following sense. So what you do is to each cell, for example, in Matthieu's thesis, to each cell, you want to construct a differential form which has poles along the boundary of the cell. Right, so you're constructing a form. Each cell gives you a form, and the form has singularities along the blue lines. And then you're going to integrate over some other space, possibly everything except for the red lines. And that's exactly dual to this picture. In this picture, your form has singularities on the red lines, but you're only integrating over the region bounded by the blue lines. And there is a way, in fact, in which they're related. So you may just think that's a trivial duality. You're just swapping the notion of boundary of the domain of integration with singularities of the integrand. But actually, there's a precise sense in algebraic geometry in which those actual integrals are related to each other. Something called Verdier duality. You can actually relate the integrals with singularities along A, along regions whose boundaries in B, with the same thing with A and B swapped around. So the amplituhedron story, as far as I can gather, is dual in precisely this sense. The forms have poles where I'm considering the domain of integration, and vice versa.
Okay, thank you. Yeah, the duality, that exactly answers. Yeah. So
I don't know if that's of help or not, but that's
yeah. No, food for thought. Another basic question, if I could. It's a more basic one. When you constructed the space by gluing together some cones.
Yes.
Right. So and then you took this quotient by the symmetry of the graph, right?
Yes.
So that is just to say, make sure I understand. Put another way, could you say that you're taking the quotient of the normal fan of the permutahedron by some group?
Getting that right? I should just first caveat that these constructions are absolutely not due to me. Like
yeah. Okay. No. That's the basic.
Quite clever that. So many authors I didn't even attempt to write it down because the list is huge. Yeah, I think that's more or less right. But when you say the permutahedron, of course, there's a different
That different one, the generalized permutohedron photograph.
Yeah, right.
Okay. Okay, cool. Thanks.
Are there?
Yeah, then this category of cones comes from the theory of toric varieties and normal fans and so on. That's where the language comes from originally. So that's right, yeah. Mm-hmm.
Are there more questions?
Hi, I have a question.
Hi, Lauren.
Hi, very nice talk. There's you're probably aware there's various higher dimensional versions of spanning trees. You can generalize a graph to a simplicial complex, and there's various analogs of I think Kirchhoff's formula. And I was just wondering if your theory also makes sense in physics, or this sort of second polynomial that you're considering, whether there's higher dimensional analogs.
Yeah, that's a great question, and the honest answer is I just don't know. I just don't know. There's a whole zoo of variants around the theme of the Kirchhoff polynomial, which is like a very specific specialization of the top multivariate top polynomials, and I think you're right that a lot of these things should generalize. But I personally haven't looked at that. I think it's something that would be very interesting to do. So yeah, I don't know.
Thank you.
Thanks. Are there more questions? Yeah, maybe. Okay, I have a couple of questions. So in summary, I think what Nick was saying was whether this fun that after you gluing these cones, if this fun is a polyhedral fun, so if you can take if there is a dual polytope to that. I think the answer was yes. Is that in general?
I think so.
Okay.
But I was saying that the point is to glue all these things together. So there isn't a single polytope. You've got a whole collection of them. Which
no, sure. What I mean is that if it's a polyhedral fun, you can interpret the fun as a normal fun of a class of polytopes, but at least.
Yeah, I'm not 100% sure. I think that's probably true.
Okay, I see. Yeah, I think in terms of polytopes, the bridge between this kind of volume picture and the canonical form is that I think the canonical form encodes somehow the volume of the dual polytope, and I think it's a polar dual. I think in terms of polytopes, it's well understood actually, like how to go from one picture to another. But for the amplituhedron it's very broad open question on how to go to the dual. So you compute the canonical form of the amplituhedron, and it somehow encodes some function which is positive in some sense, has some nice properties that should correspond to the volume or some other space, but the dual amplituhedron hasn't been discovered. So
okay.
That's what but for polytopes that should be fine. That's why I was wondering about whether these funs were polytopes, were dual to polytopes. So this is one. The second question is about the it was an interesting formula, the asymptotic factorization. I was wondering, you said that you can fix, so you're just using these factorization properties and maybe defining the seeds, then you can almost uniquely fix these polynomials, but do you also have to specify what's the behavior in the remainder functions? Like what is the order of in epsilon, or that doesn't matter, or for each order?
So the precise statement. So I've written this down somewhere in a paper. I can point you to the precise statement. So what you say is you have to every graph you pick a certain type of graph. Say these graphs, and you say to each graph I want to assign a polynomial which is homogeneous of a fixed degree.
Okay.
In the variables with whatever properties you desire. So you say, so for the first semantic polynomial, we want a polynomial that's homogeneous of degree equal to the loop number.
Okay.
And then you impose these relations, and you just say that the remainder term is of degree higher.
Higher, okay.
That's it. So that goes to 0 in the limit.
Yeah, I guess the other properties are fixing automatically the order.
I think because of homogeneity. I don't completely remember. It's a long time since I think that's. And then you find that you get down to like a trivial graph, and there's almost no, you just end up determining them up to a constant, because clearly you can multiply psi by an overall constant and it'll satisfy the same properties. When you do it with psi, you do run the same game, but now you say it's of degree 1 higher. Now, when you do that, and you've got these external legs now, so when you do that and you impose this in ultraviolet and infrared factorization I didn't mention, you find something very interesting, that the seeds are like a single edge or a graph with momentum coming in. And if you declare that to be the momentum to be Q, and you declare the edge to be M, then it generates the masses and the momentum automatically for you.
Mm-hmm. Yeah.
But there's this very interesting twist to that tale, which is that the induction is completely determined by that, except for a single new piece of input, which is for a banana graph for each loop order. There's a new room, there's a new parameter, there's new freedom of movement. So you could sort of take these Feynman rules, whatever, take these graph polynomials, and for every banana graph, you could add a new parameter and change it without affecting any of the properties, any of the combinatorial. And it's very strange that there's this extra latitude in the theory. You can have these extra parameters, one for each banana graph.
So, and what is the interpretation of this extra parameter?
I have no idea. It doesn't seem to have a physical interpretation, but it's there. Mathematically, if you ask this mathematical problem, what are the space of all possible polynomials satisfying the conditions which are known? It's completely rigid up to this extra parameter. And this parameter gives you a way to deform your Feynman integrals uniformly, or uniformly with respect to a new parameter in such a way that all the combinatorial properties are preserved. And
have you tried to consider these finite, so this differential form omega g, or like whatever you've been doing in the last slides for this deformed version, or can you repeat the same story basically for this deformed version, or?
So this other version, I don't know how to write it as a graph Laplacian matrix or anything like that.
Right, I see.
So, obviously this is an extension of the work I was doing previously on graph complexes and all that stuff. And everyone kept asking me, can you do it with momentum and masses? And I kept saying no. And then I realized that actually there's this generalized graph Laplacian to which it applies. But that's a great question. Is there a way to get this extra parameter in this matrix somewhere? I don't know. That's a great question. I haven't thought about that.
Okay. I mean, it seems that, well, it depends. I don't know actually how this construction, on what this construction relies on. But if it relies on this asymptotic factorization, then maybe it should be possible. But if it relies on specific properties of this choice of semantic polynomial, then maybe it's not possible.
No, it's just that. So there's this asymptotic factorization you can see on the whole, actually on the whole level of the entire graph Laplacian. So if you take the graph Laplacian and you allow edge variables to go to 0, it asymptotically becomes a block, block diagonal.
I see.
So that's the sort of generalized, that's the sort of fundamental reason why the factorization holds. And it's also that's how you prove that these integrals are finite. Because you sort of go into you go towards infinity and you study this factorization and check that the divergences cancel out, essentially.
That's nice. Maybe, sorry, the last brief question, I think it's kind of a broader, I suspect the answer is not known, but like just, is there any development to understand how these finite quantities are related to computation of Feynman integrals, in a sense that?
Yeah, great question. So obviously, the first thing because this work was generated whilst giving my lecture course, people were asking about momenta. So as I've been going along, I've been calculating examples, and the first sort of canonical integral that's non-trivial is the massive box with 4 particles. And you get a non-trivial, you get the Feynman integral of the massive box on the nose. That's only in 2 space-time dimensions, weirdly. 4 space-time dimensions, you get the one-loop hexagon function. Oops, can I draw a hexagon? Then you get lots of non-trivial ones. You know, this graph gives a non-trivial Feynman integral. It's interesting because in classical quantum field theory, this has a subdivergence, that the Feynman integral doesn't converge at all, but the canonical integral does. So it somehow renormalizes the integral automatically. And I've computed some other examples, the box triangle, has an interesting Feynman integral. The integrand is slightly different from the usual Feynman rules. It's an interesting integrand, and they satisfy lots of sort of Stokes relations. They're combinatorial relations between these canonical integrals. So I don't know. It's a really interesting question. Like, is there some sort of quantum field theory lying behind this? I don't know the answer to that.
Or whether there is a regularization or renormalization scheme to get to these finite.
Yeah, for example. But I mean, to answer your question, there is a significant overlap. So some of these integrals are zero, some of them vanish, just because the canonical forms happen to vanish on that graph. But a lot of them are non-zero, and you pick up a lot of very famous Feynman integrals, and they're the genuine amplitudes that people have studied extensively. So there is significant overlap with amplitudes in real-world quantum field theories that arise in this. So the meaning of this, I have no idea. Okay. It's a mystery.
Yeah.
So I have another question. Oh.
Yeah. Sorry. Yeah. I can go.
Yeah. So you have a new geometric interpretation for the second symmetric polynomial, right? Would you have any interpretation for the sum of the two of them? Does that have a meaning for you?
No, it doesn't have a meaning for me.
Because that's one formulation of that appears in one formulation of Feynman integrals. So just wondered if you would, yeah.
Does it? So the sum.
This Lee Pomeranski formulation. Yeah, that's the sum is the key object there. So
it's a while since I've looked at that. I mean, in some sense, Xi is already a sum. The polynomial Xi is already a sum of the first semantic polynomial plus. Here it is. It's already a sum of the first semantic, and this is sometimes called the second semantic. So there can be some confusion there. But the reason I wouldn't like to take psi plus this is they have different degrees. They have different. Yeah.
No, I mean that's people complain about that, but so it is.
But in some, the sort of counter is it doesn't bother me too much because psi is already some. So when psi vanishes, so it's a fact that when psi vanishes, psi automatically vanishes. So adding another multiple of psi to it doesn't change much because the geometry of how it meets. Sorry, I keep flicking back and forth. The geometry of how it meets this, I tried to draw it here. The geometry of how it meets the cells is this one, that if the cell meets the zero locus of the first semantic, then the second semantic necessarily vanishes. So adding another combination of psi to xi won't change that. And that's the essential feature, which is how they meet the boundary of the cell.
Ah, okay, interesting.
No, the answer is I haven't done that. I think one could cook it up. Just by if I were to add one here, then clearly it's gonna add the determinant of lambda g to this determinant. So it's gonna do the Lee Pomeranski thing for you automatically. Whether I want to add one, I don't know, but it doesn't bother me too much, to be honest. So I guess the answer to your question is yes. One could probably do a version.
Okay, but it's not clear what it would mean.
It's not clear what it would mean, but it would just be some variant of this construction, which I'm thinking out loud whilst you've asked me this question, but I think if one adds a constant here, that should do what you say. Because if you expand this matrix determinant, you're going to get xi plus c det lambda. That's xi plus c psi.
Yeah.
So I think it's not very far away from this story.
Okay, interesting. Thanks a lot.
Thanks. Yeah, so if you just 1 minute, I actually have another question. Otherwise,
no problem.
So can you go also to the last slide again? Sorry for bringing it. Okay. Yeah. So have you been trying to consider sums of these finite quantities over a certain set of graphs and seeing whether there is any simplification of the results, or I don't know whether, because in physics or in computational scattering amplitudes, it happens that somehow you have to sum over a certain type of graphs, a certain topology, a certain fixed number of loops, right? And then the final answer could be somehow simplified, and maybe it's easier than just trivially considering the sum of complexity of each graph. I was wondering whether the geometry might inform you of some more invariant way of writing
Yeah, so
graphs and seeing geometrically that the answer is kind of easier or something.
So I'm in terms of the first, in terms of taking the sums of graphs, of course it'd be great to write down an amplitude and integrate over the whole moduli space. So sometimes you can do that, but the issue is it's not clear how to orient the cells. So you know what the factor should be 1 over the automorphism group of the graph. It's not clear to me how you need to fix an orientation on the graphs in a compatible way, and I haven't really thought about that. So that's the only thing that's stopping one from writing down a sum of all graphs. But I agree, it would be very nice to say you just got a form, you integrate it over the whole moduli space.
Yeah.
There are issues with that because the forms aren't the right dimensions. So you're integrating over the skeleton of the moduli space. So it's a little bit more. In terms of things simplifying, actually, my suspicion is that these are the most simplified versions already, because they satisfy all these Stokes relations. They satisfy very nice combinatorial relations to do with contracting edges and so on and so forth. So I suspect that and these relations that these canonical integrals satisfy are just not true for ordinary Feynman integrals. So I think that they are already very simplified in some sense.
Yeah, I think the individual ones, I believe that they're very simple, but I was just wondering about summing over different cells.
Yeah, so I don't know how to do that. I mean,
okay.
There are ways to get around that by looking at a generating series of these integrals, and then as sort of a linear combination of graphs and the coefficients of these integrals, much like Kontsevich does in his deformation quantization. But then at the end, you've got you haven't got a number, you've got a linear combination of graphs.
I see.
So that makes sense, but it's not clear what to do with that.
Okay.
I mean, it doesn't directly connect with quantum field theory in that sense. And the issue is one of orientation.
Yeah. Okay. I see. Okay. Great. Thank you. If there are no more questions, then we can thank Francis again for the very nice talk. And also for taking more time for all these questions.
Pleasure. Thanks for your questions.
Thank you very much, and see you soon. Bye.
Bye. Thank you.